Okay, in this video what we're going to do is we're going to work on a problem set that involves just drawing Lewis structures, determine geometry, and ultimate polarity. Now all this is leading into what has been called intermolecular forces and trying to understand some of the details about the physical properties that are observed within two compounds. So in this example, what we're going to be doing is we're going to be working with methylamine and then this methylthiol group here, which is CH3SH. Now, one of the first things we do here is let's just read the problem. So it says the following problem deals with two molecules, methylamine and methanethiol. So draw the Lewis structure to determine the molecular geometry and the polarity of each molecule. So let's go ahead and deal with the Lewis structure first here. And so for this first compound, it's fairly simple. You've got a carbon and you have a nitrogen. Now the carbon, you got to follow the octet rule for both carbon and nitrogen. So we're going to have 4 bonds to each. And so now there's 4 valence electrons around the carbon. There's 5 valence electrons around the nitrogen. So just go ahead and put those in there. So we know that there's going to be a bond here in between the carbon and nitrogen. There's 3 hydrogens around the carbon, CH3. So we're going to have CH3 here, CH3, and then you have NH2, which is going to have a hydrogen here and a hydrogen there, and then you have the lone pair that comes off of that. So that's the Lewis structure for this compound. And now the next thing we do is we're going to look at molecular geometry. And so to do the molecular geometry, you have to be specific towards looking at either the carbon or the nitrogen, because there's 2 centers here. So the carbon has 4 domains, no lone pair, so that's a tetrahedral. I'm just going to abbreviate that tetra. The nitrogen has 1 lone pair, 3 bonds. That's still 4 domains, but it's no longer going to be tetrahedral. It's going to be trigonal pyramidal. Now both of these tie into the polarity, and this molecule being that you have that nitrogen, there's a difference. There's no real symmetry about this. It makes this molecule polar. So keep in mind that you have the 4 CNOF up on the top right of the periodic table. As you go to the right, the electronegativity increases, so you're going to have a dipole that pulls towards the nitrogen here. So that takes care of the first compound. Let's look at the second compound here. The second compound, same scenario. You have carbon with 3 hydrogens attached to it. Then you have the sulfur. Now the sulfur's got 2 lone pairs and 1 hydrogen comes off of it here. And so same thing here. So carbon is tetrahedral. The sulfur has 2 bonds and 2 lone pairs. That's 4 domains. And so it fits within the same group, but this molecular geometry is bent. And again, there's a difference here. There's no symmetry, which makes this molecule polar. When I say there's no symmetry, the carbon and the sulfur are obviously different from each other. They have differences in electronegativity, and that difference is what creates this molecule as a polar compound. So we have our Lewis structures drawn, and what we can use the Lewis structures for is to determine those intermolecular forces of attraction. All right, so we look at the first compound, and well, first thing here is London dispersion. So London dispersion is in everything. It's a polar compound, so it's going to have dipole-dipole automatically for that reason. Same thing goes for the other one, London dispersion and dipole-dipole. Now, the third thing we're looking for is, does it have a hydrogen bond? So remember that in order to have a hydrogen bond, you have to have 3 elements, nitrogen, oxygen, and fluorine, and a hydrogen has to be covalently bonded to that element, or one of those elements. So looking at the first compound, CH3NH2, we see that there is a hydrogen bonded to the nitrogen, so therefore that gives you a hydrogen bond. You look at this, the second compound, sulfur, is not one of those three. So what you see is what you get: London dispersion and dipole-dipole. There are no hydrogen bonds for this. Now, when we start talking about the strength of the compounds and dealing with their boiling points, we ought to see a stronger since we see strong attractions within the methylamine group, that should have a higher boiling point. So looking at the last little bit in this problem set, it says the boiling point of methylamine is negative 6.3 degrees Celsius and plus 6.8 degrees Celsius for methane thiol. Are these data consistent with the statement that hydrogen bonding is one of the strongest of intermolecular forces? So looking at the boiling point, it looks to be, based off the information here, that the methylamine has a lower boiling point than the methane thiol. Now, that goes backwards from what we just said, right? And the fact that the question is, are these data consistent with the statement hydrogen bonding is one of the strongest of intermolecular forces? And the answer is no. All right. So in this case, it's a clear example as to the methane thiol has a larger boiling point than the methylamine. Now, so what could be the reasoning behind this? Well, if we look at the structures, surface area also does play a role, along also with molar mass. So these other variables that go beyond the intermolecular forces do tie back into this. So it's most probable that the surface area for this CH3SH is higher, and so the molecules are able to mesh together tighter, and if they create a tighter complex with each other, then they're going to have a strong interaction. It's going to be harder to break that interaction. It's kind of like holding hands. If you hold your arms at your elbows versus holding hands, your elbows are going to be much harder to break because there's more surface area there in comparison to holding hands. So going back to this, surface area would be the best explanation for this, because surface area, again, if you have the molecules are tighter fit together, they're going to be harder to pull apart in the very end, and that could offset the difference there and make these have the differences in their boiling points and the physical properties. So now other properties that you could look at are viscosity and surface tension, but again, that's not a part of this problem. But you could think about how would the viscosity of the methane thiol differ from the methylamine itself. So, but for now, we're just focused on what the questions are being asked. So I hope this will help you a little bit in reference to just understanding how the Lewis structures tie into the intermolecular forces, and then ultimately those physical properties that we observe.